We've sent over 100 missions to the moon. We've walked on it, driven on it, crashed things into it on purpose. And somehow, the more we look, the stranger it gets. If you find that as fascinating as I do, hit like and subscribe. Because what the latest science is revealing about our nearest neighbor will completely change how you think about it. Here's the thing most people don't realize. We've been studying the moon longer than almost any object in the solar system, and yet some of the most fundamental questions about it, what's inside it, why its two halves look completely different, where its water actually comes from, and whether the ground beneath future lunar bases might literally shake them apart, remain genuinely unsettled. These aren't fringe mysteries. They're headline findings from peer-reviewed journals, from missions costing hundreds of millions of dollars, from instruments lowered carefully into lunar soil by robotic arms controlled from Earth. And every time one question gets resolved, a stranger one opens up beneath it. To understand why this matters, you have to start with the simple assumption that drove half a century of thinking. The moon is dead. After the Apollo astronauts came home, after the samples were analyzed, after the seismometers went quiet, and the last rover tracks filled with dust, the scientific consensus settled into something comfortable. The moon is a cold, dry, geologically inert world, a relic, not a living body. It formed, it cooled, it stopped. That was the story. And for decades, that story went mostly unchallenged. Then we sent better instruments, and the moon started talking back. The first puzzle that deserves your full attention is water, or more precisely, the extraordinary and deeply confusing way the moon appears to have it everywhere it shouldn't. This story has been building since 1976, when the Soviet Lunar 24 mission drilled 2 meters into the lunar surface, extracted about 170 grams of regolith, and shipped it back to Earth. When scientists ran their analysis, they found something unexpected: traces of water, roughly 0.1% by mass. And more interestingly, the deeper the sample came from, the more water it contained. At the time, almost no one took it seriously. The moon was dry. Everybody knew that. The water had to be contamination from Earth, from the equipment, from the journey. The result was filed away, and the assumption held. It held through the Apollo era, which returned samples also showing trace hydrogen-bearing compounds, but which were likewise dismissed. It held until the late 1990s, when a mission called Clementine, originally designed not to look for water at all, mapped large portions of the moon's poles and revealed something that would eventually become very important. Certain craters near the poles were in permanent shadow. The moon's axis is tilted only about 1.5 degrees, so the sun always skims sideways across the poles. The deeper the crater, the easier it is for sunlight to miss the floor entirely. There are places on the moon that haven't seen a single photon from the sun in nearly 4 billion years. And if anything containing water had ever landed there, a comet, an asteroid, even micrometeorites, the ice could, in theory, survive indefinitely. This idea gave birth to a new mission in 1998. NASA's Lunar Prospector Orbiter carried a neutron spectrometer, and it found exactly what scientists hoped: high concentrations of hydrogen near both poles, especially in the permanently shadowed regions. The numbers were striking, somewhere between 10 and 300 million metric tons of water equivalent. But there was a problem. Hydrogen alone is not water. Lunar Prospector couldn't distinguish between H2O and hydroxyl, or OH, which is a close chemical cousin, but not the same thing. The instrument said something hydrogen-bearing was there. It couldn't say what. So NASA took a dramatic approach. At the end of Lunar Prospector's mission, they deliberately crashed the spacecraft into a shadowed polar crater, hoping the impact would kick up a plume of ice that Earth-based telescopes could detect. It didn't work. No water signature appeared. The mystery deepened rather than resolved. Then, in 2008, India's Chandrayaan-1 mission changed the picture. Its onboard moon mineralogy mapper, a NASA instrument, detected the spectral signature of hydroxyl and water molecules on the lunar surface from orbit. This was the first orbital confirmation that some kind of hydration existed on the moon beyond just the poles. And the following year, NASA's L-Cross mission took the boldest step yet. It crashed a 2-ton Atlas Centaur rocket stage directly into Cabeus crater at the South Pole and flew a shepherding spacecraft through the resulting debris plume. This time, the results were unambiguous. The plume contained water vapor, hydrogen, ammonia, methane, carbon monoxide, and carbon dioxide. Most critically, the hydrogen signal from Lunar Prospector was confirmed. There was actual frozen water in the soil of that shadowed crater. Scientists estimated the permanently shadowed regions collectively could hold around 600 million metric tons of ice. The moon was no longer dry. That was settled. But then things got stranger. In 2020, NASA's SOFIA observatory, a modified Boeing 747 carrying a 106-inch infrared telescope that flies at 45,000 feet to get above most of Earth's atmospheric water vapor, made an observation that nobody expected. It pointed at Clavius crater, one of the largest craters visible from Earth with the naked eye, located in the moon's southern hemisphere. Clavius is not in permanent shadow. It receives substantial sunlight, and SOFIA detected for the first time ever the specific molecular signature of H2O. Not hydroxyl, not a general hydration signal, but actual water molecules at concentrations of 100 to 412 parts per million. To put that in scale, a cubic meter of lunar soil in Clavius crater contains roughly the equivalent of a 12-ounce bottle of water dispersed across it. The Sahara Desert, by comparison, is about 100 times wetter than what SOFIA found. The lunar surface is extraordinarily dry, but the water is there on the sunlit surface, where by every previous model it should not exist. The lead author of that 2020 paper in Nature Astronomy, Casey Honable, put it plainly. Without a thick atmosphere, water on the sunlit lunar surface should just be lost to space. Yet somehow it's there. Something is generating it. Something must be trapping it. Two leading hypotheses involve micrometeorite impacts fusing lunar minerals into tiny glassy beads that can physically trap water molecules, and the solar wind, a constant stream of hydrogen ions from the sun, reacting with oxygen in lunar minerals to form OH, and eventually H2O in situ. But neither mechanism is confirmed as the primary driver, and neither fully explains the observed distribution. The question of where this water comes from and how it survives remains open. This brings us to the second puzzle, which in some ways is even more disorienting than the first. In August 2023, India's Chandrayaan-3 mission accomplished something historic. The first successful soft landing in the moon's south polar region, touching down at 69.37 degrees south latitude. Among its instruments was ChaSTE, the Chandra's surface thermophysical experiment, a thermal probe equipped with 10 temperature sensors that was slowly inserted 10 centimeters into the lunar regolith over a 29-hour controlled process. What it measured fundamentally changed how scientists understand the moon's thermal behavior. At the surface, ChaSTE recorded a peak temperature of around 355 Kelvin, about 82 degrees Celsius, which is actually slightly higher than models predicted, partly because of the probe's location on a sunward-facing slope. That's hot, but not surprising. What was startling was what happened at depth. In just 10 centimeters of descent, less than the length of an index finger, the temperature dropped sharply. The thermal conductivity of the lunar regolith was measured at approximately 0.0115 watts per meter per Kelvin. That is extraordinarily low. For reference, aerogel, one of the best thermal insulators humans have ever manufactured, has a conductivity only a few times lower. The top few centimeters of lunar dust act as a near-perfect thermal blanket. The implications are significant and somewhat surprising. A surface baking at 80 degrees Celsius can be sitting on top of material that, just a hand's width below, is substantially cooler. Previous Apollo-era measurements of heat flow existed only for equatorial regions. Chandrayaan-3 provided the first in-situ thermal data from the high-latitude South Polar region, the very region where future astronauts and robotic missions are expected to operate. And what those measurements suggest is that the model of where water ice might persist needs revision. Poleward-facing slopes greater than about 14 degrees, the data implies, could harbor water ice even where direct orbital surveys haven't clearly confirmed it, because the insulating regolith above keeps the subsurface cold enough, even if the surface itself receives some sunlight. The ice, in other words, might not be where we've been looking. It might be buried just centimeters deeper than our instruments reached. This is consistent with a frustrating pattern that has emerged across decades of lunar exploration. The L-Cross plume came from below the upper soil layer, not the surface itself. Apollo and Lunar samples showed increasing water content with depth. Orbiters detect hydrogen signals that surface samples don't always match. Each time scientists design a mission to look at the surface, the evidence suggests the interesting material is just slightly below where the instruments reach. It raises an uncomfortable and genuinely open question. Are we consistently searching at the wrong depth? The third puzzle is perhaps the most unexpected of all, and it comes from the moon's deep interior, a region no mission has ever directly sampled. When China's Chang'e 6 spacecraft landed in the South Pole Aitken Basin in May 2024 and returned 1,935 grams of far-side lunar material to Earth, it made history as the first mission ever to bring back samples from the moon's far side. The South Pole Aitken Basin is the oldest, deepest, and largest confirmed impact crater in the solar system, approximately 2,500 kilometers across and 8 kilometers deep. Scientists had long believed that material from this basin, if retrieved, would reveal something fundamental about the moon's deep interior. They were right, though not entirely in the ways they expected. 4 landmark studies based on these samples were published in the journal Nature in 2025, and together they told a deeply strange story. The most striking finding involved water. Scientists measured the water content of the far-side lunar mantle for the first time using apatite minerals and melt inclusions in the basalt samples. What they found was a mantle source containing only 1 to 1.5 micrograms of water per gram of rock, far lower than the values found in near-side lunar mantle samples, which range from roughly 1 to 200 micrograms per gram. The two hemispheres of the moon do not just look different. They are chemically different all the way down into the mantle. This is called a hemispheric dichotomy, and it has been observed in lunar surface features for decades. The near side of the moon, the face that always points toward Earth, is covered in vast dark plains called Maria. ancient lava fields from billions of years of volcanic activity, a relatively thin crust, and high concentrations of radioactive elements like thorium and uranium. The far side is almost the opposite: heavily cratered, thicker crust, far less volcanic activity. Scientists have proposed various explanations for this asymmetry, including the possibility that Earth's gravitational influence concentrated heat-producing elements on the near side during the Moon's formation. The Chang'e 6 findings now extend that asymmetry into the Moon's interior water distribution, and they are consistent with the giant impact hypothesis, the widely accepted theory that the Moon formed from debris blasted into orbit when a Mars-sized body called Theia collided with the young Earth about 4.5 billion years ago. The geometry of that collision, models suggest, would have produced exactly this kind of internal split, with volatile elements like water being distributed unevenly between the two hemispheres from the very beginning. The Moon appears to carry the scar of its own violent birth all the way down to its core. The same Chang'e 6 samples also revealed that volcanic activity on the far side was far more prolonged than anyone realized. Two distinct eruptive phases were identified, one around 4.2 billion years ago, and another as recently as 2.8 billion years ago, meaning volcanic activity on the lunar far side continued for at least 1.4 billion years. And the samples captured something even more surprising: a rebound in the Moon's magnetic field intensity around 2.8 billion years ago. The Moon no longer has a global magnetic field, but these paleomagnetic measurements showed that 2.8 billion years ago, the field briefly strengthened rather than simply declining. That suggests the lunar dynamo, the internal process that once generated the Moon's magnetic field, did not simply fade steadily. It fluctuated, it pulsed. The Moon's internal life was more dynamic than anyone thought. But it is the fourth discovery, the one that directly affects every future human mission to the Moon, that may be the most consequential of all. For decades, the dominant scientific picture of the Moon's interior was essentially static, a world that had long ago finished cooling, finished moving, finished doing anything geologically interesting. The Apollo seismometers, which operated from 1969 to 1977, recorded thousands of vibrations, but many of those were attributed to thermal expansion, meteorite impacts, or tidal forces from Earth. The Moon's geology was considered settled, dead, done. What NASA's Lunar Reconnaissance Orbiter has revealed since 2009 is something fundamentally different. Its cameras have imaged more than 3,500 lobat scarps, cliff-like fault features that form when a world's crust compresses and one section is thrust up over another. On Earth, we see features like this in regions of active tectonic compression. On the Moon, they are caused by something else. The Moon is slowly shrinking. As its interior cools over geologic time, the entire body contracts. The crust, rigid and brittle, wrinkles and breaks. Scarps form, and critically, the LRO images show that many of these scarps are geologically young, formed very recently in the Moon's 4.5 billion year history, possibly within the last 50 million years. Some show bright patches at their bases that indicate freshly exposed material, which darkens rapidly in the lunar environment. Fresh material means recent movement. A 2019 study, led by Thomas Waters of the Smithsonian Institution, used a new algorithm to re-examine the Apollo-era seismic data and match shallow moonquakes to specific fault locations. They found that 8 of 28 shallow moonquakes fell within 30 kilometers of a mapped thrust fault scarp, close enough to attribute them to fault slip. 6 of those 8 quakes occurred when the Moon was near apogee, its farthest point from Earth, when Earth's tidal pull on the lunar crust is at maximum stress. The Moon isn't just shrinking passively. Its faults are being triggered by its ongoing gravitational dance with Earth, and those faults are still generating earthquakes, or rather, moonquakes, right now. This is not an academic concern. A 2024 study focused specifically on the South Polar region, the target of NASA's Artemis missions and China's Chang'e 7 and 8, found that the strongest shallow moonquake ever recorded by the Apollo network had its epicenter somewhere in the lunar South Polar region. The exact location could not be determined precisely, but the cloud of possible positions overlaps with several of the Artemis 3 candidate landing sites. The same region is threaded with lobat scarps, and computer modeling shows that some areas near these faults are susceptible to regolith landslides from even moderate seismic shaking, a serious concern for any permanent infrastructure. A December 2025 study published in Science Advances went further. Scientists used boulder falls and landslide deposits near the Lee-Lincoln Fault Scarp, the same feature Apollo 17 astronauts physically drove their rover over in 1972, to estimate the magnitude and frequency of past moonquakes there. They found that magnitude 3.0 moonquakes have occurred repeatedly along that fault over the last 90 million years. That fault, they concluded, is still active. For a short mission, like Apollo 17, which lasted 3 days, this is essentially no risk. But for a decade-long lunar habitat, the statistics change significantly. A 1 in 20 million chance of a damaging moonquake on any given day becomes a 1 in 5,500 chance over 10 years of continuous occupation. The researchers were direct about the implication: don't build near a scarp. And then, in February 2026, yet another study extended this picture further. Scientists published the first worldwide map of small mare ridges, subtle tectonic features in the Moon's dark volcanic plains, showing that they are young, widely distributed, and linked to the same compressional forces that produce the lobate scarps. The Moon's tectonic activity is not limited to a few known fault zones. It is a global, ongoing process. And the seismic hazard zones it creates are far more extensive than previously mapped. A world once described as dead is, it turns out, still contracting, still quaking, still changing. What all of this adds up to is a picture of the Moon that is dramatically more complex than the one we thought we had. Water exists not just in the permanent shadow of polar craters, where we expected it, but in the sunlit surface, where physics says it shouldn't survive. It is present as ice, as molecules trapped in glass beads, as traces in ancient volcanic minerals, and now as a deep internal feature that differs between the Moon's 2 hemispheres. The regolith is such a perfect insulator that ice may be hiding just centimeters below warm surface soil in regions our instruments have not yet reached. The Moon's interior has 2 faces that are chemically distinct all the way to the mantle. A fingerprint of a 4.5 billion year old catastrophic impact that shaped not just the Moon's surface, but its very core. Its magnetic field once pulsed and rebounded rather than simply dying. Its geology, the faults, the scarps, the seismic hazard zones, is not a relic of the distant past, but an ongoing feature of a world that is still, slowly, physically evolving. Every one of these findings was the result of a specific instrument, a specific mission, a specific measurement that pushed past what previous technology could do. The Soviet drill that pulled up 170 grams of lunar soil in 1976 was not taken seriously enough. The Indian probe that slid 10 centimeters into lunar regolith in 2023 changed thermal models for the entire South Polar region. The Chinese spacecraft that returned 1,935 grams from a crater billions of years old redrew the internal map of a world we thought we understood. The Apollo's seismometers that recorded data from 1969 to 1977 are still being reanalyzed with new algorithms, still yielding new answers about moonquakes that happened while Neil Armstrong and Buzz Aldrin were still alive. This is what makes the moon one of the most scientifically valuable objects in the solar system. Not because it is distant or exotic, but because it is close enough to study with high precision. And because every time we look more carefully, we find that the simple story is wrong. The moon is not dry. It is not geologically dead. It is not simply split across its visible surface. It is a world with a complex, still unfinished history, hiding its most important secrets a few centimeters underground, or in the internal chemistry of rocks nobody has touched in billions of years, or in the slow groan of a crust cooling and cracking around a still warm interior. For anyone planning to live there, and multiple space agencies are now actively planning exactly that. These are not abstract scientific curiosities. Water distribution determines where a base can sustain itself. Thermal properties of the regolith determine how deep you have to build to stay warm or cool. Seismic activity determines where it is and is not safe to anchor permanent infrastructure. The moon is not simply a destination. It is a dynamic environment, and we are still in the process of understanding it. The questions being asked right now, in the papers being published right now, are the same questions that will determine the success or failure of the next era of human space exploration. That is what makes them worth paying attention to. That is what makes the moon, even after more than 100 missions and over 50 years of scientific inquiry, still genuinely, compellingly, wonderfully weird. If this changed how you think about the moon, drop a comment below. What surprised you most? Was it the water hiding in plain sunlight, the moon still shaking beneath our feet, or the fact that its two sides are chemically different all the way down to the mantle? Subscribe for more deep dives into the science that is reshaping what we know about the universe. And we'll see you in the next one.